All right, let's get started on chapter 3, numerically summarizing data. Okay, so in section 3.1, we're going to look at measures of central tendency. So we're going to look at the arithmetic mean, describe what that is. We're going to look at the median, describe what that is, the formulas for it, how to interpret it. We're also going to look at the mode and define resistance and what that means in general. Okay, so let's start with the mean. The arithmetic mean of a variable is computed by adding all the values of the variable in the data set and dividing by the number of observations. So the arithmetic mean is usually what we think of as the average. Whoops. The average. Right? When you know, in everyday life, when people talk about the average, this is normally what they're talking about. The average in everyday life is really what we call in statistics the mean. Okay, so we don't use that word in statistics, but that's what it is. Okay, so the arithmetic mean is going to be a situation where you're given all the values of a set, and you're going to add them together and divide by the number of values in that set. Okay, so first thing we have to do is identify that in statistics, we are going to always have a population that we deal with, and we're going to have samples of that population, right? So we usually have a population. Now, usually the population is very large. It might be like the population of all Californians, or it might be the population of all employees of a big company, like let's say Walmart or something, a huge company that has thousands of employees, right? It could be the population could be a product, maybe all vehicles manufactured in the year 2013 for some reason, right? So usually it's very large, but it doesn't have to be large. It could be small. It just depends on how you define it. So every word problem you work with, you got to be careful about how they're defining a population. The population could be my students in this class, and that's it. So not that many, right? The population could be the number of people that have walked on the moon, very small population, right? Or the number of people that have ever been into outer space. Okay, slightly larger group, but still fairly small. Okay, when we look at our population, once you've identified it and defined it, there will be characteristics of that population that we want to find. One of them is the mean. Whenever we take characteristics of the population, all of those are called parameters, right? So anything about that population that we know, how many values are in there, the mean of those values, and we're going to define many other things in this chapter. But anything about the population is a parameter. Now, from that population, we will take a sample, right? Hopefully a random sample, so that hopefully this sample is a good representation of that population, right? That's our hope. So this is like a little microcosm of the population, so that we can find characteristics of this sample and then make inferences about this population. So like, for example, if the population is all Californians, millions of people, right? And then we take a sample of, say, 1,000 people. We want to be able to find out something unique about those 1,000 people and then be able to make an inference about all Californians. Say, for example, average income. We have millions of people in California. We want to know the mean income. Well, okay, so we take the 1,000 people that are in our sample, we find the mean income of those people, and then we want to be able to say something, make some sort of guess about what the population mean income is going to be. Good? It's usually the setup we're going to have. Okay, when we are dealing with sample values, then the characteristics of the sample are called statistics with a lowercase. Okay? All right, so when we're dealing with the mean of a population, we like to use this little notational symbol, which is called mu, M-E-W, mu, pronounced as mu. it looks like a squiggly M. Okay, so this little mu symbol always means the mean of a population. Good. The mean of a sample is going to be this X bar. X with a little bar on top of it, just X bar is how we pronounce it. And it's the arithmetic mean of a sample, right? So any characteristic of a population is called a parameter. Any characteristic of a sample is called a statistic with a lowercase s. With a capital S, statistics is a branch of mathematics that we're learning, right? That's statistics. Whereas a statistic is a characteristic of a sample. And the mean of the sample is just one example, one type of statistic that we can find from our sample. Good? So the mean from here, the mean of a sample is X bar. The mean of a population is mu. Okay? Always. So if you're just given that mu equals to 7, for example, without anything else, you already know that this refers to a population. Or if you get that X bar is equal to 6.2, well, that refers to a sample, right? Just because X bar always refers to a sample. Given a static population, right? Let's just a population that doesn't change. Just we write them down. Here are our values. We take samples. Well, the mean of the population doesn't change, but of course the mean of the sample can change every time we take a new sample, right? So keep that in mind as we move forward. That the samples kind of depend on the values we take in here. So say, for example, this is, I don't know, let's see, all members of Congress, right? 435 members of the House. Say 435 members of the House. There's 1, 2, 3, 4, dot, 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 all the way out to 433, 434, 435. Right? So we list them. I'm not going to list their names, but here they are, all 435 members of Congress for a particular year. I don't know, let's go back in time and say in the year 2012. So all members of the House, and okay, here they are. And we might take a sample of 20 of them. 1, 2, 3, dot, 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 19, 20. So 20 members of the House are randomly selected. Okay, and we could be looking for something about their mean. How about the mean height? That's interesting. Mean height, right? I don't know if you're aware of this, but there's this thing about politicians being a little taller than the average person. Something about people just trust tall people, or maybe tall people just kind of have a sense of leadership or something. People want to follow the tall people. I don't know. But the mean height of politicians tends to be a little higher than the mean height of the rest of the population. So that's interesting. So let's say we find the mean height of all the congressmen and women in the year 2012. So let's say, and I'm just making up numbers here just to kind of prove a point. Let's say that mean height is, I don't know, and I'm just making up stuff. Let's say it's 6'1". 6 feet 1 inch. Okay. All right. So now we take a sample of 20. Maybe in that sample, it doesn't necessarily mean that sample is going to have exactly 6'1". It might. It's possible. It's not impossible for it to happen. Oops. It might be that the sample is exactly the same as the population. But it could also happen to be the case that it's just a little bit different. Maybe in our sample, the mean height was exactly 6 feet, 0 inches. Right? Or maybe in our sample, maybe our sample was just a little bit different. Maybe it was 2 inches. Right? It depends on which of those 20 people was selected. It would be a little weird for it to be very far off, right? Because the mean sample is 6 foot 1 inch, that doesn't mean everybody in here is above 6 feet tall. There might be a few people that happen to be kind of on the short side, right? There might be one person in Congress that's 5 foot 4 inches, right? But there's also going to be one person in Congress that's like super tall, 7 feet 3 inches, maybe, like a super tall person. It's possible. We're saying the mean of all of these people is about 6 feet 1 inch. Okay, so when we take our sample, this is a little microcosm of that. So it would be unusual, unlikely perhaps, that our little sample happens to target all the short people and we end up with the mean height of our sample that's very different, very low compared to the mean of the entire population, or the other way around. It would be kind of weird for too many of the tall people to end up on our sample and then this to be very different. So if it's a truly random sample, if the sample is large enough, hopefully that sample does a fairly good job of kind of representing the population. Some tall, some short, And so we're hoping that the sample mean is very close to the population mean, right? That's a big focus of what we do in statistics. But this stays constant, and the samples change, right? So now let's say I take another sample. We call this sample number 1. But we could go, okay, now let's take another sample. Sample number 2. Sample number 2. And so a whole new batch of people, 1, 2, 3, 19, 20. Whole new batch of people are selected. It's likely that this result has a slightly different sample mean. The mean here, x bar, is going to be a little bit different. Maybe this one happens to be 5 foot 9 inches, right? Kind of close, but a little on the low side. This one's a little on the high side. And then, well, how do we distinguish these two? We introduce these little subscripts, right? So let's call this sample 1. Let's call this x bar sub 1. And this one, x bar sub 2. And so on and so forth. Good. The mu, we usually don't put a little subscript unless we have a completely different population as well. So like maybe this is mu sub 1, which is the Congress, House of Congress in 2012, but maybe we have a completely separate population, which could be the Congress in 2014. Population, right? Another group of 435 members, 2, 3, all the way out to 433, 434, 435. Okay, and so now these people would have their own mean. It's a population, so it would have its own mean. And now to distinguish these two, well, then maybe we introduce that subscript, mu sub 1, and then this one we could call mu sub 2. Right? So you just have to be careful about the notation. Notation is a really big deal in statistics. These are really difficult concepts, so we have to develop sophisticated notation to be able to express our ideas. But then, of course, learning the notation is part of the challenge of learning statistics. Okay, so these little subscripts are important. Pay attention to those. And don't make the mistake to think that this has anything to do with squaring. Right? This is not, this little 2 here doesn't mean we're going to square anything. It's just part of the label. It's just part of the name. Okay? All right, moving on then. The formulas. All right, well, we all know what the average is. Just add them all together and divide by the number of entries. So that's the formula for both the mu, the mean of a population, as well as x bar, the mean of a sample, right? Look, they're both kind of identical formulas. All you have to do is add up the entries and divide by the number of values. The only thing that's a little bit different is 2 things. One, of course, we use the mu to identify that it's a population, and we use x bar to identify that it's the mean from a sample. And also, this little subscript here, n. Remember that capital N represents the number of values in a population, n observations of variables from a population, whereas lowercase n is the observation of a variable from from a sample. Okay, so let's say that we were talking about, you know, some population where n, let's say n equals to 8, right? It doesn't have to be big. It could be a small group of people, right? Like the number of people that have ever walked on the surface of the moon, for example. And I don't know if it's 8 or not. It's probably not, but it's a small number. So if we have a population like this, then let's say the first value in my population has the number 2. The next value in my population has the number 3. The next value in my population has the number 4. The next value in my population has the number 7. The next value in my population has the number 9. Next value in my population has the number 13, number 17, and finally x sub 8 has the number, I don't know, -3. Okay, so in order to find the mean of these 8 values, the formula states that all we have to do is add all of these together, and divide by the number of entries. So this could be 2 plus 3 plus 4 plus 7 plus 9 plus 13 plus 17 plus -3, and divide that whole thing by the number of entries, which is 8. Okay, so what is that? That's going to be 5, 9, 16, 25, 38, 55, 52. Mu equals to 52 divided by 8. And so let's check that that's true. 2 plus 3 plus 4 plus 7 plus 9 plus 13 plus 17 minus 3, 8. So mu equals to 6.5. Easy formula, right? Just in general, if there are n of them, we use capital N to refer to how many there are. On the other hand, if we're talking about a sample, our sample might have only 4 values. Maybe our sample has n sub 1 equals to, say, I don't know, 8, x sub 2 has 4, x sub 3 has -2, and x sub 4 equals to, I don't know, 0. Okay, so here lowercase n equals to 4. Well, as you see, the formula is identical. All you have to do is add the entries, which is 8 plus 4 plus -2 plus 0. Divide that by 4, and we get 10 divided by 4. Good. So x bar equals to 2.5. Okay, pretty easy equation, right? Let's move on then. For example, the following data represents the travel times in minutes to work for all 7 employees of a startup web development company. Okay, so somebody took 23 minutes to get to work. Somebody took 36 minutes to get to work. Another person also took 23 minutes. Then someone took 18, then 5, then 26, then 43. Compute the population mean of this statistic. Okay, so the key here is that it states all 7 employees, right? This is everybody. That makes this a population. If, on the other hand, they said this company has 1,000 employees and they randomly selected 7 of them, then that would be a sample. So we would be computing x bar. Okay, so this is very straightforward, right? We know that the formula is going to be mu, population mean, is going to be 23 plus 36 plus 23 plus 18 plus 5 plus 26 plus 43, all of that divided by 7. Okay, so just go over to your calculator, add those values together. 23 plus 36 plus 23 plus 18 plus 5 plus 26 plus 43. I'm getting 174. 174 divided by 7. I get that mu equals to 24 points. Let's go to 4 decimal places. That's 8574. 8574. Oops, 71. $85.71 going out to 4 decimal places. Okay, that takes care of part A. Part B says, take a simple random sample of 3 employees, compute the sample mean, obtain a second simple random sample of size 3, obtain and compute a sample mean. Okay, so we get the idea. If we randomly select a few of these, now how do we randomly select a few of these? Well, if we had a 7-sided die, we can roll it and randomly pick which ones get selected. We can also use technology to randomly select some of these values. So for the moment, I don't want to deal with the technology or something to do that. We can also just put all these numbers, individual little pieces of paper, into a hat, reach in there, grab them, pull them out, and be able to randomly select them that way. So let's just skip that part for now. And let's say sample 1, after randomly selecting them, is going to be a 5, a 26, 3, and a 23. Maybe that's sample 1 after randomly selecting these. Sample 2, 1, 2, 3. Maybe we randomly select 43. Notice that we wouldn't be able to pick the same person again, right? That wouldn't make sense for this. So once the 43 has been chosen, that person is removed, and now there's 6 more values to choose from. Maybe the next one is 26. Maybe the next one after that is 36. Good. Okay, so now we find the sample means for each one of these. And so the formula is very straightforward. So the formula is going to be x bar sub 1, sample 1, is equal to 5 plus 26 plus 23 divided by 3. So x bar sub 1 is going to be equal to 31 plus 23, 54 divided by 3. 4 plus 26 plus 23 divided by 3. 18. So 54 over 3, x bar sub 1 equals to 18. Okay. On the other hand, if we take another random sample sub 2 is equal to 43 plus 26 plus 36. X bar sub 2 is going to be equal to 43 plus 26 plus 36 divided by 3. We get 105 divided by 3. 105 divided by 3. So x bar sub 2 equals to 35. Notice how far away these are. The mean of the population was 24.8571, but sample 1 gave us a result of 18, and sample 2 gave us a result of 35, both fairly far off from the 24, right? Okay, so we see that that's not totally uncommon. It has to do a lot in this case from the fact that it's a fairly small sample And the numbers kind of vary quite a bit from 18 to 43. There's a lot of variation there. And also the sample size is fairly small at just 3. Therefore, it's very susceptible to being influenced by one or two large numbers. It just so happens that in this sample, a lot of the larger numbers were selected, right? And in this sample, the smallest value was selected, so that had a big impact, right? Oh yeah, 18 from 5 to 43, pretty big difference. Okay, all right. So that's exactly the same thing that the author did. Add them together, divide, we get that, and then we compute samples. Okay, let's move on. Another way to measure a group of numbers besides the mean is something called the median, right? They're both measures of central tendency, sort of where's the middle of the data. One way to describe the middle of the data is by finding the mean, the average that we just worked with. But another one is this one, also very, very important, very popular, the median. The median of a variable is the value that lies in the middle of the data when arranged in ascending order, right? Ascending order is from the smallest to the largest, right? Ascending. The other one is descending, going from the largest to the smallest. So you're given a set of values. The original raw data might not be arranged from the smallest to the largest. So part of the work you're going to have to do is to organize them from smallest to largest. And then the number that's right in the middle, physically in the middle, not the actual value of the number, but the actual number right in the middle of the list is going to be the median, right? We use capital M to represent the mean. I'm sorry, to represent the median in statistics. Good, pretty good. Okay, so how do we find that? Well, okay, let's first of all write down some examples of what we're talking about. So let's say that we have a very small list and they're already in order. So say, for example, we have the numbers 3, the numbers 5, 7, 82, and 103. Okay, wait, so they, say we have these values here. Okay, so they're in order from the smallest to the largest. We're going to have to label them. This thing's really messy. I'm going to erase this whole thing. Okay, so let's say we had 1, 2, 3, 4, 5 numbers, and they're already in order. So the original list might not be presented to you this way, but you're going to have to put them in order. So let's say we had the numbers 2, then 7, then 13, then 19, then 28. We have these numbers. Okay, the one right in the middle, we can physically see that it's this one, right there. That's the one in the middle, therefore that's the median, right? When we put them in order, the one that's right in the middle. Notice that there are 2 numbers this way, and there are 2 numbers that way. So it makes sense that that one has to be in the middle. Good? And that has nothing to do with the actual values. The 13 is the median, right? Median equals 13. But notice that if I came back here and erased something, like let's say instead of 28, it was 112, right? A much bigger number does not affect the median. It's still 13, right? It's the one right in the middle. Likewise, we can come back and change one of these numbers. Maybe instead of a 2, it's negative 28, right? Much farther to the left. Does not affect the median, right? The median is the middle number, and that does not affect it. What does affect it is if we add another number, because then this will no longer be the one right in the middle, right? So if now, for example, we come back and we, let me see. Let's say we come back and we look at that, but then we add a couple extra numbers. So now let's say we have another number there and another number there. So let's say that this is the number 172 and the number 201. Okay, well now the 13 is no longer in the middle, right? Now adding more values did change it. If we added 2 more numbers, now it makes sense that the 19 is the one right in the middle. That's going to be the new median. Notice that there are 1, 2, 3 numbers this way, 1, 2, 3 numbers that way, 3 numbers this way, 3 numbers that way. It makes sense that this one is going to be the median. Good, median, and it equals 19 in this case. Good, good, good. Okay, so the actual numbers don't go into the calculation of the median. The number of spaces is what determines what the median is. Okay, so here we had 1, 2, 3, 4, 5 numbers, and the median was the value in the third spot. Good. Here we have 1, 2, 3, 4, 5, 6, 7 values in our set, and the median is the one in the fourth spot. It would be exactly the same if some things change a little bit. So now, for example, if instead of a 19, it wasn't a 19, it was changing it to a 34, it doesn't change the median. Why? Because, again, as long as we're still in the same order from the smallest to the largest number, there's still 7 entries, so the median is whatever number is in the fourth spot. Good. It could still be even bigger. It could be 84. The median would still be 84 from this set. The only time where changing it would affect things is if this one, if we change that and go, oh, we made a mistake. It wasn't actually 84. It was 114. Well, now it changes because now that means that this guy is over there, right? We have to order it from the smallest to the largest, and then the 1/12 would become the median. Okay? All right, so I hope that's clear. All right, well, as long as we have an odd number of entries, we're always going to have a number that's right in the middle and it's perfect and divides up our set in a way where we have an equal number of entries to the left and an equal number of entries to the right, right? So here is our set of instructions for finding the median. We're going to arrange the data in ascending order from smallest to largest, right? Smallest to largest. Got to do that first. A great way to do that, by the way, we learned before, is the stem and leaf display. If you look those up, that makes it a lot easier to organize numbers, a set of values from the smallest to the largest. Okay. Determine the number of observations that are in our set. How many observations do we have? And then we want to find the value right in the middle. Now this part here is the hard part, step 3. Find the observation right in the middle. And that's going to break up into 2 different set of instructions based on whether or not there are an odd number of entries or an even number of entries. Okay, so if we have an odd number of entries, if the number of observations is odd, just like in the previous 2 examples I just did, one of them had 5 entries, one of them had 7 entries, there was an odd number of entries. Okay, then the median is the data value exactly in the middle of the data. That is the median that is in the observation that lies in the n+1 divided by 2 position, right? So coming back up here to this example, there were 5 numbers, right? Here n is equal to 5. And so the median is the value in position. Median is the value in position. And then there's a little formula for the position. It's n+1 divided by 2, right? So for us, that would be 5 plus 1 divided by 2, That's going to be 6 divided by 2 or 3. The third position. And that's what the answer was right there, 3. Good. For this example, right, that's one example. For this one, n was equal to 7, right? So the median is the value in position n plus 1 divided by 2, which is going to be 7 plus 1 divided by 2, which is 8 divided by 2, which is 4. Yep, the fourth position. The number, the 114 is the median. Keep in mind that the 3 is not the median, the 4 is not the median. This little formula just tells you the location where you can find your median. It's the fourth spot, the value in the fourth spot, the value in the third spot. Okay, that works great as long as we have an odd number of entries. So if you're dealing with a very large set, let's go back over here. So for example, if we're dealing with a very large set, and I know that I can organize them, and I know that I have, you know, number 1, number 2, number 3, dot, 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 and way out there. So let's say that there are 117 different numbers from the smallest to the largest. Okay, that's a lot of numbers. Well, there's an odd number of values, so this can tell me the location of where my median is going to be located. So if n equals to 117, odd, then the median is going to be the value. Median is the value in the n plus 1 divided by 2, or 117 plus 1 divided by 2, which is 118 divided by 2, which is 59, right? The 59th spot. The 59th spot in my ordered list. Okay? So once I organize them, the actual values in my data set from the smallest to the largest, maybe the smallest number in my list was 13. The second smallest number in my list was 13.2, and so on and so forth. I got to keep going. And the one right in here, in the 59th spot, whatever that is, right, whatever this is, that will be my median. Okay, that works great as long as we have an odd number of entries. But what if we don't have an odd number of entries? What if we have an even number of entries? So for example, let's just say we have 4 numbers. 1, 2, 3, 4 numbers, an even number. 1, 2, 3, 4. And let's say those, it's a small list, so let's just make some stuff up. Let's say that this is 7, 9, 11, and 17. Okay, so here's my 4 numbers, an odd number of values. Well, where should the median be? Well, it can't be the 9. If I choose the 9, if I choose that 9, then there's only 1 number to the left and 2 numbers to the right. So that's not a fair assessment of the middle. If I choose the 11, I have the same problem in the opposite direction, only 1 number over there and 2 numbers over here. So it seems fair that it should be somewhere in between the two, right? Somewhere there would give me 2 numbers to the left and 2 numbers to the right. So what I have to do is find the mean of these 2 values. I'm going to take 9, the median is going to be equal to the 9 plus 11 divided by 2, which equals to 10, right? The 10 will be my median. And notice that in this case, the median is not even a number in our original list. I'm not inserting the 10 in there and saying, oh, now there's an extra number. No. The original list had 4 values. That's the number of entries in our set. But the 10 is the median, even though it's not really a number in our result. Okay. All right. So now, how do we figure out like a little formula to describe how to find it? No, I know that 9, 10, 11. It seems like kind of a nice little coincidence there. But notice that this would have changed. So like, let's say, for example, I don't want you to get the wrong impression here. Instead of an 11. Let's say that that number was an 11, it was 15. that still puts it in order, so that as long as it's not bigger than 17, the order stays the same. Okay, so now the median is going to be the mean between these two numbers. So I'd still have to come back over here and change that, which would change that. So this would now be 9 plus 15, which gets me to 24 divided by 2 equals 12. So now my median changes to 12. Good. Okay, so I have to find those two numbers that are sort of in the middle and then find the mean of those two numbers. All right, let's do one more where we have more. Let's say we have 6 values. So let's say we have 1, 2, 3, 4, 5, 6 values. So there's 1, 2, 3, 4, 5, 6 values. And it doesn't even matter what those numbers are yet. It would make sense that in order for us to find the median, it'll involve these two, right? These two are in the middle. There's 2 numbers that way, 2 numbers that way. I'm going to have to find the mean of these 2 numbers. Good? Good. Let's do one more. What if we had 8 of these guys? What if we had 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so now in this case, again, it would make sense that it would be something to do with these 2 guys. That way there's 3 that way, and there's 3 that way. Okay, so when there were 4, what's the connection between a 4 and then these 2, a 2? What's the connection between when there's a total of 6 and this guy, the 3, and when there's 8, then this guy, the 4? Is it clear that every time we have an even number of entries, if we half it, that number divided by 2 gets you the first of the 2 that we need to find our mean of? Good. So if I told you there's a total of 6 values on my list, we already know that the value in the 3rd spot is the first one I got to deal with, and then the one right next to it. Good. So if I have a large even number of entries, 1, 2, 3, way out there. Let's say I have, let's say we have 102, an even number, right? 1, 2, 3, all the way up to 102. Then following this formula, there will be 2 numbers that kind of qualify as the values I got to deal with. And from my pattern, that first one in that list is going to come by taking this number and dividing it by 2. This one will be 51, the 51st number. And well, just the one right next to it. So then the next one right next to it will be 52. Right? To be clear, I'm not going to find the mean of these 2 numbers, 51.5, no. I want to find the results that go in there, the numbers in my list, the value that's in the 51st spot, plus the value in the 52nd spot, add those 2 together and divide by 2, right? We want to find the mean of these 2 numbers, and that'll be the median. Okay, so that's what this little expression is trying to say. If the number of observation is even, right? So let's say let me put it for n number of entries. 1, 2, 3, right? 1, 2, 3, all the way out to n. 1, 2, 3, all the way out to n, and it's even. Then the 2 numbers we care about are going to be the 2 values that are right here, where the first one is going to be n divided by 2. Take that number and divide it by 2. That gets you to the first one. And then the one right next to it. The one right next to it is going to be n divided by 2 plus 1. N divided by 2 plus 1. That'll tell you the number that belongs there. We take those two values, whatever they are, add them together and divide by 2. We want to find the mean of those two values. Okay, so that's what this set of instructions is telling us. Let's go back to this example. The following data represents the travel times in minutes to work from all 7 employees of a startup web development company. So we already worked with these numbers. Somebody took 23 minutes to get to work. Somebody took 36. Another person also took 23, 18, 5. Okay. So there are 7 observations. That's an odd number. If there's an odd number, that means that there's a perfect value right in the middle. Right? So we first of all have to put it in order from the smallest to largest. 1, 2, 3, 4, 5, 6, 7. Okay. From smallest to largest. 23 was repeated, so we copy it again. Good. And it makes sense that following our formula, the value in the 4th spot will be our median. 1, 2, 3, 4. That's this guy right there. It makes sense because there's 3 that way and 3 that way. It's right in the middle, right? The median is the middle value. So the median, which we like to use this m, oops, not the mu, which we like to use m, is equal to 23. Cool, 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 cool. All right, that's when there's an odd number. On the other hand, let's say, suppose that the startup company hires a new employee and the travel time of the new employee is 70 minutes. Wow, this person's really commuting. Determine the median of the new set. Now we have a brand new person in there, so that means that there are an even number of entries. Now there's 8, that's even, right? So following our little formula, we half that, and that'll get us to, why did I do this? N plus 1 divided by 2. Okay, I'm not sure I like that, but okay. So we get the 8 plus 1 divided by 2. That's going to give us to 9 divided by 2. That's a decimal, right? Wait, why am I... Okay, so n is equal to 8 is even, right? So we know, just kind of to visualize it, to kind of just envision it, 1, 2, 3, dot, 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 all the way out to 8, right? And we know that the perfect values are going to come from finding the mean of the 2 numbers in the middle, and the first number is this one divided by 2. 8 divided by 2, which is 4. It'll be the 4th number on my list. And then the one right next to it, which will be 4 plus 1, the 5th number on my list. Right? So this is from the formula of n divided by 2. Right? N divided by 2, that's the 4. And then the n divided by 2 plus 1, which gives you plus 1 gives you the 5. Okay, so if we put them in order from smallest to largest, then that means that the 4th spot is going to be the 23. 1, 2, 3, the 4th spot. And then the 5th spot's the 26. That's why we take 23 plus 26 divided by 2, we get 24.5, and that's our median for the set, 24.5, a number that's not even in the original set. Good. Okay, the following data represents the travel times to work of all 7 employees of startup web development company. Suppose they hire a new employee that has a 130-minute commute. How does this impact the mean and the median? All right, so if we toss in an extra person, right, one new extra person in here, 130, how does that impact the mean? All right, well, the mean before hiring the new person, and this is all 7 employees, so that means that the mean is a mu, right? It's everybody, it's the population. Well, we did that before. 23 plus 36 plus 23 plus 18 plus 5 plus 43, all of that divided by 7. So we'll get that mu was equal to, I think we had that up here somewhere. Awesome. 24.8571. $24.8571. Okay, and then the median. All right, well, if we organize them from the smallest to the largest, we already did that before. We found that this would be 5, then 18. Then there's two separate 23s, 23, 23. Let's see, that takes care of that guy, then 23, 23. Then there's 26. Then there is 43, 36 and 43. 36 and 43. There's my list. And so we found before that the median is going to be this guy right here. That's the one right in the middle. 3 numbers that way, 3 numbers that way. Right? There are 7, n equals to 7. So the median is the value in the 7 plus 1 divided by 2 equals to 8 divided by 2, or 4. The 4th position, 1, 2, 3, 4. Okay? Median. Right? And this is all before the new hire. All right, what happens after? After, okay, so now how does that change this? What just happened? Okay, so how does that change this? Well, we're adding an extra person. So that means we have to add the extra person afterwards. There's an extra plus 130. And now instead of 7, there's a total of 8. Right, so we've got to add all those numbers, divide by 8. So mu now equals to 23 plus 36 plus 23 plus 18 plus 5 plus 43 plus 130. 278 divided by 8. 278 divided by 8. Which gets me to mu equals to 34.75, right? So this had a fairly large impact. It really changed the value of mean from the before to the after. What about the median? All right, so all right, so now when we're thinking about the median, all right, so that's just going to add one more number way over here at 130. Toss that guy in there. Scoot this over a little more. 130. Okay, well that means that now we have 8 entries instead of 7. So instead of this being the median is going to be the mean of these two numbers, right? There's 3 that way and 3 that way. So 3 different numbers. 3 that way, 3 that way. It's going to be the mean of those two, right? That's because now n equals to 8 now, which means that we're going to have to deal with the value in the 4th spot. 8 divided by 2 equals to 4, right? That's the formula, n divided by 2, and the n plus 1, n divided by 2 plus 1. which is going to be the fifth spot. Okay, so we take the 23 plus the 26 divided by 2, and that gives us 23 plus 26 divided by 2, 24.5. 24.5. Okay, so that's the new median after we toss in the extra worker. Median equals to 24.5. Okay, so what's the difference, the before and after? Well, the mean changed a lot, went up by 10 units, right? It's a pretty high increase. Versus the median went from 23 to 24.5. So it still went up, but not by as much as the mean. Okay, so we say that the median is more resistant to uniquely large values, and also in the other direction, uniquely small values. So we call those outliers, extreme values. The extremely large, the extremely small, extreme values, we also call them outliers. The median is more resistant to change by those things. Okay. Let's see if we 24.5 and 38. Uh-oh, did I do something wrong? (23 plus 26). 23 plus 36 is 23 plus 18 plus 5 plus 43 divided by 8. (23 plus 36 plus 23 plus 18 plus 5 plus 43 plus 130. Okay, so a numerical summary of data is said to be resistant if the extreme values, the very large or the very small, relative to the data, do not affect its value substantially, right? It might have a small impact, but just not a dramatically large impact. Relationships between the mean, the median, and the distribution of the data. Okay, so we can consider a distribution that looks like this, right? Now, what you should be thinking here is kind of like, think of like little marbles. Each little marble has a number on it, so that if more than one marble has the same value, then we kind of stack them up above each other. That's what you can kind of visualize for this, meaning that the taller it is, the more times we see that value. Good. So this means that over here, we see these numbers very little because it's not very tall over there. And then in the center, it's the tallest. We see those entries the most. And then again, we start to see less and less of them as they go over here. So the horizontal axis tells you the value that's on the marble, and the vertical axis tells you how often we see that value. So that it doesn't go very high, it means we don't see it very often. There's very few of those. Whereas if it goes really high up, that means we see a lot of those. Okay, so this is a symmetric distribution, right? There are just as many values going in this direction as they are in this direction, kind of equally distributed. This is also considered a bell-shaped distribution, symmetric. In this kind of distribution, the mean is going to be equal to the median. Good. On the other hand, if we have a case like this, where there are a few extreme values to the left, and not as many extreme values to the right, then we say that this has a left skew, a left tail, right? And notice that the mean is more sensitive to those outliers. So it gets heavily impacted by those numbers, more impacted by those numbers than the median. So when we have a skewed left data set, the mean will be to the left of the median. On the other hand, if we have a distribution like this one, it means that there are a few outliers over here, unusually large relative to the rest of the data, and those numbers are having an impact on the characteristics of the entire population, but they impact the mean a lot more than they impact the median. Good. So, for example, if you're thinking about salaries of people, right? So this over here indicates that there's a certain, there's no numbers on here, so it's just kind of describing the situation rather than the specific numbers. For low salaries, right? The horizontal axis describes the salary amount. 10,000 a year, 20,000 a year, 50,000 a year, 80,000 a year, 100,000 a year, 120,000 a year, something like that. Well, this is saying that there are very few people over here in those low numbers, and it climbs up to some max that's the most common value, maybe 90,000 a year. And then it begins to climb down, 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 down. But this is saying that there's a few people that are way, way, way over here in the multi-millionaires. So when we find the mean of salary, the few people that make a lot of money really impact the mean salary of everybody, right? If we took the mean income of all faculty members at our school plus Bill Gates, well, Bill Gates' mean salary is going to be so much larger than the rest of us that when we find the mean, it's going to be some huge number, right? Between Bill Gates and our faculty, our mean salary is probably about $10 million a year, something like that, just because his salary is so huge compared to us. On the other hand, if we are going to consider the median, then the fact that we tossed in his number is not going to impact things as much, right? Just based on how we calculate the median. Okay, so that's what this means. So the median is a characteristic that's more resistant to outliers, right? Going back to this definition, resistance. Good, good, good. There's a nice little applet for this on your account, so let's look at that. Okay, log on to your account, go down here where it says Multimedia Library, and then go right here where it says Applets, and then go to Chapter 3, Mean versus Median. Let's check that guy out. And just a little applet that kind of shows you how you can play around with these things. So let me make this a little larger. Okay, so here is a number line from 0 to 8. So I can just kind of add in values into here. So I can put a little ball there. It looks like it's a little bit higher than 4. Why is looks to be having a little bit of a hiccup here. Reset. Well, it seems to be having a bit of a hiccup because I can see that the little ball I've selected seems to be visually it looks like it's a little bit past the 4, but it's identifying it as 3.965. So numbers are a little bit off, but that's okay. It doesn't matter. We just got to get a sense of what it's doing. Okay, so let's say I have something like this, where I have this little distribution, 3 there, and then 2 there, and then something like this. And then, okay, it's not letting me choose something. But at any rate, this is equally distributed, right? It's symmetric. It builds up to one tall thing, comes back down. There's just as many numbers there and here. So when we have a nice, pretty symmetric thing, the mean is equal to the median. If we toss in an extra one over here, now it's going to be off a little bit, right? That one extra number there changes the mean from the median, but if we put it over there, we should go back to being, the same. And it's a little off, just a tiny little bit because of a computer error here. But now let's say we toss in one large number over here, then the mean is more heavily impacted by that large number, right? See how it kind of goes toward it a little more? We put in a number over there, put in another number over there. See how the mean is being dragged over by those large numbers a little bit faster than the median. The median hasn't changed much for this set. But I can keep tossing them in there. And even after all those numbers, the median just hasn't changed very much. It's being dragged over, but kind of slowly, right? Whereas the mean is just heading that way. It's being heavily impacted by the fact that we have those extra values over there. On the other hand, if we come way over here and start stacking some values on the opposite end, it'll attract the mean in that direction as well. So let's add a bunch of those over there. And eventually we get back to a point where the mean and the median are pretty close together. Again, right now we have more of a balance as well. Okay, so the mean is more easily attracted to the extreme values, whereas the median is a little bit more stable. Right? The median is more resistant. Okay, so here's an example. The following data represents the asking price of homes for sale in Lincoln, Nebraska. Okay, so we have all these homes from sale from the smallest to the largest. They've already been listed from smallest to the largest. The cheapest house for sale is $79,995, and the most expensive house is $349,900. Okay, find the mean and the median using a TI-84 calculator, then use the mean and median to identify the shape of the distribution. Verify your results by drawing a histogram of the data. Okay, so here's an opportunity to use our calculator. When we are dealing with a very small data set, you are expected to write down your work. So as when the test comes along, if I give you a small number of values, it might say, show your work, do it by hand, and that just means that you do something like the work I've been doing so far. So if I ask you to find the mean and do it by hand, I expect to see this written down on the test, at least the setup of it. You don't actually have to add these by hand, right? This is not an arithmetic course. But I at least want to see the setup of it. Set it up like this. This is how you found it, and you did that. The median. Again, if it's a small set of values, I expect to see this. Write them down, point out which one it is, maybe like a quick little blurb about the little formula and how you knew that that one was it, the little formula. Or a little sentence. The median is the number found in the fourth spot. That's when they're small. But when you're dealing with a much larger set like these, that's hard. I don't want you to write it all out. That's just a waste of time. I'll expect you to use your calculator to be able to do these problems. Okay, so how do we do that? Let's go over to our TI-84 calculator. Okay, so let me make that bigger. Turn it on, hit clear, no matter where you're at, hit clear. And then you might be in a weird screen, so we want to exit. Or quit from whatever screen you're on. So if you're stuck in some screen you've never seen before, like that, and you're like, what is that? That's what happened when I turned on my calculator. We want to quit and get back to the main screen. And that's found right there, right above the mode. Let's see if I can make this even bigger for now. Right above the mode, there's this little button that says quit that's written down. Okay, so the same button will have two functions, the one that's written on the button, that's mode, and also it could be whatever is written in color right above there. So if I hit second, then quit, it'll get out of that screen and bring me back to the main screen. So looking at these, for example, if I just click this 5, notice how the little box is blinking. If I hit 5, it'll type in 5. Okay. On the other hand, if I want to type in the letter U, I gotta hit alpha, which makes it this green button, and then you'll see a little A blinking to let you know that the alpha button has been locked. And now if I come back here and hit the 5, it's not gonna do 5, it's gonna do a U. Good. And then there's the L5. Well, if I want L5, it's in blue, it's the second, so notice how it's a little box blinking. Now if I hit the blue, it's a little up arrow blinking. That's to let you know that the second has been activated. So now if I click 5, L sub 5 will be selected. Okay, so that's how we deal with this. See all of this clear? Okay, so the first thing we have to do is list all of this stuff into our calculator. We're going to be working with this a lot, so it's important to remember this. Once you go to your main screen, so turn it on and hit clear or quit, whatever, get back to the main screen. You're going to go over here where it says stats. That takes you to this screen. Okay, and then this is a little menu. You can use your arrows. You can go to the left. I'm sorry, you can go to the right. You can go to the left. And then underneath each one of these, you see a bunch of selections that you get to choose from. Okay, so it just so happens that the very first one we want is the one we want. So number 1, edit number 1. So you can either hit 1, and that'll take you there, or you can hit enter, and that takes you to this. You should see L1, L2, L3, L4, L5 written at the top. If you don't see those, if one of them is missing or something, then let's fix that right now. What you want to do is go back to stat and hit setup editor, hit enter, done, and that'll fix it. Stat, edit, enter, and you should now see all of them in there. Okay, all right. We'll see why they wouldn't be there in a second. So let's type in some of these numbers in, and we want to put all of it in one big happy list. So 79,995 is one of them. 99,899 is another one. 105,200 is another one. 111. And finally, $349,900. Okay, so that's the hardest part, putting them all in there. It's tedious. You got to be real careful of typing them all in there. One big long list in here. Should have 32 entries. So if you notice the notation here, list 1, L sub 1, and then has a little parentheses 32, so that this is the 32nd entry. You can come back over here and double check that you've typed them all in. And there should be 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4. There's 32 numbers in here, 32 numbers in there. They match. We're all good. Okay, so now that you have everything on your list, that's the hard part. Now we're going to find the mean and the median using our calculator. So we're going to hit this button again that says stat. And then we're going to go over to the right where it says calculate. And we want to do the very first option, 1 var stats, 1 variable statistics, 1 var stats, hit enter. Next, it's going to tell you, well, what list are we working with? Yeah, we're working with this list, L1. So hit enter. Frequent list, make sure this is blank, right? Blank. And then hit enter. And then we're going to hit calculate. Back and we'll go through that. So let's put that. And here's our result. The X bar value, the mean, is equal to this value. And then to find the median, we have to go back down. So use these arrows. And there's the median. Okay, so the median is 148,700. And the mean is 168,320. Notice that the calculator has written X bar. The calculator always uses X bar. There's no way for the calculator to know whether you're talking about a population or a sample. So that's up to you to decide whether this should be mu or X bar. But your calculator will always write down X bar. So keep that in mind. Okay, so let's match that up with the results that the author got, and they match. The mean is $168,320, and the median, go down here, is $148,700. Good. Okay, so our results match with what the author got for the same set. Okay, creating a histogram. All right, well, if you create a histogram with your calculator, you'll see that it looks a lot like this. Okay, I'm not going to cover how to create a histogram with your calculator, so don't worry about this. I won't be asking you to create histograms with your calculator, but the histogram would look like this, which would indicate that it's skewed to the right. Good. There's a few more values out here, sort of extreme relative to the center of this. And notice that that matches up with our relationship between the mean and the median. The mean is to the right of the median. Right? So the mean, which is this guy, is somewhere over here, mean, whereas the median, which is this guy, is somewhere over here. The mean is to the right of the median, right? Indicating that there's outliers over here that are attracting the mean, right? There was that one expensive house or those few expensive houses that are dragging that mean all the way that way. Hopefully that makes sense. Think about house prices here in Los Angeles. If you think about, kind of envision in your head what you think is the average, the mean cost of a house, the mean price of a house in Los Angeles, well, it greatly varies, right? But every once in a while, when you're kind of tossing in the mean price, well, one of those $50 million mansions that that sells over in Malibu, that's going to greatly affect the mean price of a house. So the median might be a better indication of where the center of the data, right? What does it cost to buy a house in the area? I think that would be better described by the median rather than the mean. Okay, the last thing we want to look at is something called the mode. The mode of a variable is the most frequent observation of the variable that occurs in the data set. A set of data can have no mode, one mode, or more than one mode. If observations occur more than once, we say that the data have no mode. Sorry, if no observations occur more than once, then we say that the data has no mode. Okay, so here's an example. The data on the next slide represents the vice presidents of the United States and their state of births. In which state were they born? Okay, so we got John Adams, born in Massachusetts. We got Thomas Jefferson, born in Virginia. Aaron Burr, born in New Jersey. Okay, so what we do is we figure out which of these states occurred most often. So we do a tally. Here's a tally. Right, this little bar here represents that somebody was born in Massachusetts, and then somebody else was also born in Massachusetts. Right? As we kind of go through these names, we had Massachusetts. Okay, so we put a little dash through Massachusetts, 1. And then the next one we see is Virginia. So we come over here and we put Virginia, 1. Okay, so we can create a tally, and from the tally, when we total them, we look for the ones that happened a lot. So we got 8 there. That's a lot. And then that's it. That's the one that occurred most often. So New York is going to be the mode. The mode is the one that happened most often. Okay, so the mode is New York. All right, so here's a nice little summary of the 3 things we discussed that impact the center of the data. Right? What is the middle of the data? One way to do that is with the mean, which we most often think about as the average in everyday life, the mean. But then there's the median, the middle, right? Think of middle, median, middle, the middle of the data. Put them in order, find the one right in the middle. And then the mode is the one that's most frequently observed, right? The one that happens most often, the one that happens mode often. So that we can get some sense of what the middle of the data is that way.